nomination, and this came from a former student. Galen's approach to teaching provides students with a glimpse of the rigors of upper division classes. His instruction allows for better preparation at four-year universities, making his students more comfortable and more acclimated when they do transfer. Being a former student and a transfer of his, I am more comfortable and better prepared at my current university due to Galen's dedication and love for teaching chemistry. I don't think there's anything better that a chemistry instructor can have as a testimony.
To be honest, not really.
Oh.
People that know me well know that I don't speak well in front of people, believe it or not, unless I'm talking about chemistry. But I do need to thank a lot of people. I don't know where to start. I guess with the section for choosing me, that you must have had a really shallow view.
There are something like 23 community colleges in the section, so it was a wide view.
Well, y'all need to advertise or something. And I need to thank Karen Frindell, I think, for nominating me. I think I need to thank her. But my family, my friends, my colleagues, I mean, here's 8 better recipients right here. So, thank you all very much.
We're going to take a picture after. Okay. We'd also like to acknowledge Lee Bowles, who was our high school, one of our high school chemistry teacher winners. We seem to have some excellent teachers up in this neck of the woods. Okay. In your honor, we're going to have a show now. Professors Lang and Showalter are well known in the chemistry community for having very great ideas on how to make chemistry interesting, fun to watch, and sometimes very exciting, depending on how things go. So I give you Professor Lang and Professor Showalter.
It's really a pleasure to be here at Sonoma State. It's the first time I've been here in this community, and I'm impressed. I'm impressed with this campus. I'm impressed with the hospitality we've already received, the number of people who have made us feel extremely welcome. Eileen, gotta stand up. She's made us feel very, very welcome. We've even stayed in her home to be able to do these things. We've been driven around by Paul, the chair of the local section, Mark Frischberg, way in the back over there from Santa Rosa, and he lives in Santa Rosa. It's just amazing, and all of the hospitality we've gotten here, even just today. What we wish to do is to talk a little bit about, in fact, I think the title of our talk this evening and presentation is Boiling Cold and Freezing Hot. I'm trying to let that sink in for a moment. Boiling cold and freezing hot. What happened to Bonnie Carpenter? She was here. Oh, she's hiding back there. I was just wondering where you went. You were standing. Within the ACS, American Chemical Society, you begin to form some long-term friendships. I've been involved in the society. For the first time, they've now gotten away with no dues. I've been there for so long. They don't want my money anymore. So that means I've been there a long time, and I've gotten to know an awful lot of very, very fine people. And many of them are out here in California. This particular device that you see in front of you is called a DEWAR, D-E-W-A-R. And
before we get started, Galen, why don't you stand up again? And we want to thank you ourselves. We are our university professors, and I can tell you from experience that by having my students come to me through the community college system made a big difference in my life too. It made it a lot easier for me. I want to thank all of you people that are here from the community college for all your efforts. It really is a tremendous effort. And also, Lee, where's Lee? Well, you can't imagine what it is for us as the people that taught general chemistry, and then later on for the people that come in and take the other advanced courses, what if they had the preparation from, and especially with the high school. And I think you probably would testify too. Where they first get their very first experience is at high school, and if it's bad, it stays with them. If it's good, it stays with them. So you are so very important. So thank you for all your efforts.
There's a company in Connecticut, and many of you may have heard of it, Educational Innovations. How many have heard of that? There's a young lady up in front over here, or close to the front, Sienna Parrish. She has some cards here. If you haven't gotten a card, see her. She'll give you a card. You'll fill it out. She'll collect it. And it puts you on a mailing list for and you get the catalog. But a lot of the things that we're going to be using tonight came from that particular organization. They're very, very helpful. And so I'm just bringing it to your attention.
All right, one more thing before we get going. I saw your goggles on. It's a good thing. We would try to practice safe habits too. So if you see one of us take our glasses off, so make sure you tell us to put them back on. That's always tell my students. No. I always tell them you should say thank you for caring. See, put your sunglasses on. Thank you for caring. Okay, what do you got?
I've got some elemental stuff. Is there a periodic table in this room?
There is right there.
There you go.
Now,
And is that one color coded?
what does the red mean? Gases. What's this blue means? Oh, don't have blue.
80, that's 34.
Now, where's the other blue?
There you go.
What does that mean? Liquids. And then what's the black? Solid. What's this? Glow in the dark.
It's interesting, they've now got numbers all the way up to 112 named. How many know the most recent one, 112?
Who knows those?
What's the name? That's right, 112, named after Nicholas Copernicus. But they wanted to make it CP. And the reason they couldn't? CP stands for cyclopentadienyl. So they made it CN. Well, this particular doer, one that's not silver, in front of you, of course, is two pieces of glass, an inner and an outer, and they pull the air out, so it's a vacuum, and so in a way it's insulated. But you can see the liquid is really boiling, isn't it? But it's liquid nitrogen. We know that that's very cold, so this is boiling cold. Or it could be freezing hot. Now, the
Anybody know
inside,
the boiling point with nitrogen?
77 Kelvin.
77 Kelvin. What is it in Celsius?
-196.
-196. -196. That's close enough for German. How about Fahrenheit? -321. The reason I say -320 again Fahrenheit is because you realize that the temperature of the room here is like something in the 70s. And so we're something like 400 degrees below room temperature by going in there.
What did you say it was? Minus
196 Celsius.
196 C. Almost a little degrees.
-321 Fahrenheit and 77 Kelvin.
Okay.
It's in there. What are you going to do with that, Marvin?
Well, I thought we would change some properties. What's this property?
What's the property called? What physics? Not bouncy. I'll give you a hint. It's in your underwear. Elasticity. This is elasticity. All right, now, what happens if we push the ball into liquid nitrogen? Some people will say it will freeze. Well, freeze means going from a liquid to a solid. It's already solid, so it's going to get cold. Is it very cold? Anything else you might think? It might lose some of its properties, huh? Mm-hmm. You think it will? Have you seen it before? No. You're going to see it tonight, buddy. All right.
You gotta let me
What else he put in there? Now, what's going to happen to my banana?
That's his banana for supper.
Yeah, it's something. It's going to freeze. Because what's the major component of the banana? Water. Over 90% water. And so it's going to freeze in there and it's going to become very hard. How hard? hard as a hammer. So what I'm going to do, I'm going to use that banana, once it gets down to temperature, to be able to put a nail in a board with the banana. So if you go in tomorrow and somebody says, what did you do last night? He says, well, I went to this chemistry program. Oh, what did you see? This guy drove a nail in the board with a banana. Now, if he says, he's not listening to you. He says, you just saw what? Then you'll know.
I think there's a board down over there.
I got a board. I need a right-handed glove.
Oh,
I got a board. I do have a couple holes in there because I have done this before, but I would promise you I will not put it in there.
you're not going to use an old hole.
No. What do you think? Is it hard enough yet?
Yeah.
If mine is 321, it gets harder pretty quick, doesn't it? Can you guys see that I'm not putting it in one of these holes? Okay. This is with a banana. I worked as a carpenter one summer. What they call me, Ali?
Lightning.
Lightning. Not because I was so fast, because I never hit the same spot twice. I've built the most crooked houses you ever saw. Now, I drove that in that board with a banana. See this? You couldn't get it. That thing is really in there. In fact, I had Dale. He had to get it. Well, how'd you get it out? Took a hammer.
With a
Hammer, get it out. How can we do that? It's because of the difference in temperature, that gives the difference in the properties of that banana that's involved in it. Now, one thing with that banana, where'd you put that banana? Right there. What's going to happen to that banana once it warms up? It's good, and we can tell Paul. Paul helps us clean up. It's a mess.
It is a mess.
It's a mess. It's really liquid. Now you can make it banana bread, probably put banana bread. That's about it. But what happened to it? Why did it get liquid after that? Well, what happens is that there's cells in the banana, just like we have cells. And what's in the cells? What's bathed in the cells? Water. Now, what happens to water when it freezes? It expands. And so it breaks the cellular wall, and what that does is it ends up giving you a burn, a blister, sort of a type of idea. So what do we call this when it happens at home, when we have some food we put in the freezer? Freezer burn. That makes sense, doesn't it? Freezer burn. But the idea is because it causes the same sort of an injury as if you would burn yourself because it was breaking the burst of the cells. Okay, what else?
It has door that it's got a lot of condensate in it, but the contents inside is terribly low temperature, but yet the outside is just kind of cold because it's reasonably well insulated. And you can see it simmering up here. And so I brought the racquetball to a simmering, boiling liquid nitrogen temperature. Now you do that with potatoes, do you not? You put them in the boiling water, it changes its properties. You check the seed, you put a fork in it, and it slides in, it's done. Well, I wonder how we can tell if this is done. Better do it quick. This thing is right against the door.
I put holes in walls before. Ready? You can hit the door with it.
Don't touch it! Don't touch it!
I got it. It bounced off of the wall, off of the door, but did you hear it shatter when it hit the floor? It went in. Hey, Robert, I got a glove. Oh, there we go. Oh, there's one.
Where?
Right here.
Aha! This is the important piece.
Yep, I think that's it.
Oh, and we could use a banana split up here.
Okay.
There was a suggestion of a banana split, but I have one also. I've got the piece that says pen on it. I was looking for the container, but I believe we put that aside. The container has a guarantee on the side. It does. It says if any pen ball should fail before the label wears off, send it back and they'll give you 2 new ones. So it's cold, but send it back.
All right, what up? happening here? My breath, huh? Blew into there. I like to visualize chemistry. You like to visualize chemistry? I like to think about it. Now, think about inside the balloon. Why is the balloon pushed out like that? What's happening inside there? Molecules moving around, hitting the sides, aren't they? With pressure, we say pressure in physics is force per unit area. We still do that. Chemistry don't. But how's the force generated? Molecules hit. And we look at the number of collisions hitting in a particular area that we talk about in there. So we think about the molecules in there moving at a fast rate. We can actually calculate by using formulas what the speed of a molecule of, say, nitrogen in the air. If you do it at an ordinary room temperature, something about 68 degrees, it comes out about 1,100 miles an hour. That's it. That's faster than Paul goes on this interstate. But so you imagine the molecules hitting in the inside of the balloon. Are they hitting out here too? Sure, atmospheric pressure hitting them. And so the pressure must be equalized right now because the balloon's not expanding or contracting. All right, now what will happen if we take the balloon and pour the liquid nitrogen on it? It's going to, yeah.
Pick your feet up in front.
This is an excellent audience. So no one put their hands on their ears because they know it's not going to expand, it's going to contract. So you know that as the temperature decreases, the speed of the molecule decreases, and so the balloon, it collapses because it's not being hit as often inside there. All right? And so the cold temperature, those are good balloons, so they don't...
Sounds like cellophane, doesn't it? Now, the one thing that we didn't mention when we shattered that racquetball is the properties of the racquetball underwent a change. And in polymer chemistry, when it goes under a specific phase change, they call that the glass transition temperature. It's the same thing with this balloon. It's essentially the glass transition temperature.
Mark it down pretty good. Collapses pretty good, huh?
Now, if we see through, we would find probably a little liquid in there. That liquid is probably liquid nitrogen that's on exhale from the breath.
Now what's happening? What do you visualize? The molecule's speeding up, hitting the balloon more often, and it should go right back up to the same size. It's because the temperature of the room hasn't changed. And so we had the number of moles in there constant, didn't we? Now, what variables did we change? We usually talk about pressure, volume, and temperature, and number of moles. We kept the number of moles constant. We changed all the others, didn't we? Did we change the volume of the balloon? Sure. Did we change the temperature of the balloon? Sure. But did we change the pressure of the balloon? Not atmospheric pressure, but inside there. You like
I
that?
don't like it.
Mark's a physical chemist.
I like it when you're going to have three variables, pressure, volume, and temperature. You should really hold one of those variables constant and see what the effect is. Pressure, say, versus temperature, or volume versus temperature. Remember all those laws? Boyle's law, Charles' law, and Avogadro's law, blah, blah, blah. We can do them.
Blah, blah, blah. That's the ideal gas law.
Here we have a constant volume. What's the pressure inside right now?
Atmospheric pressure.
Atmospheric pressure, same as the pressure outside. Remember that one Pepsi-Cola demonstration that they used to do? Kids walking along the beach and he's got a bottle of Pepsi in a straw. Oh, Mommy, he did it again. He gets sucked right into it. Well, what we're going to do is put a hard-boiled, peeled egg. I'm going to use it as a sealant.
But you use the word that we don't use in chemistry.
Well, there's several of these people are physicists.
We never use the word suck in chemistry. We never say chemistry sucks. Right?
Okay.
All right, so what's going to happen now when I put it inside that thing? Don't you tell me that it's going to be sucked in. There you go. Good. It's pushed in because we're lowering the pressure inside by lowering the temperature. If we lower the temperature, then the pressure, that is how many times the molecules are hitting the bottom of the balloon, has decreased. They're not changed out here, so it evenly pushes the egg inside the balloon, inside the Erlenmeyer glass. I don't want to. It hits the bottom and it freezes. All right, now I've got it inside there. Now let's use a little deductive reasoning how I get it out there. Sure, if I cool it down to get it in, I heat it up to get it out, right? And notice I haven't been touching that thing for a few minutes because it's really cold. So I'm gonna, if I put my warm hands on there, and I got a good seal, I audibly would get that egg come out of there. Is it moving?
Yeah.
Every time I do this,
Just think, right here at Sonoma State during an event called National Chemistry Week, Don Showalter is laid an egg.
oh yeah. I do this. I take those 4 chickens. This is kind of hurt. Thank the Lord they made this shape.
Can you imagine if they were cubic? It hurt.
I don't know if you ever came on the farm. If you've ever been in a hen house, it's noisy. You know why? They're all grunting. This hurts.
Why don't we help him? Can we grunt? Oh!
Oh, I think
You
we
got
got
constipated when you're. Oh!
You need warmer hands.
I need warmer hands. Hands are cold. All right, switch. Oh, forceps. We laid an egg. Now, you know, fun with it, but remember what happened. What happened? What's gas law? What variables did we keep constant? Volume and number of moles. We varied the temperature and the pressure. As the temperature decreased, what happened to the pressure? And what do we call that in math? What kind of relationship? A direct proportion. He said, well, okay, see, we learn. We can teach gas laws right from these couple of experiments. So if you're learning with us, you can teach gas
How
laws.
can I remember that?
What? As far as the gas laws?
Yeah.
Gas laws are PB over T equals NR, right? PB equals NRT. Well, the way you remember that is peas and vegetables go on the table. Got that? I'll stop.
That's as bad as his joke about 2 sodium atoms walking down the street. One says to the other one,
Wait, how many people have heard that joke? Not too many. Go ahead.
2 sodium atoms walking down the street, one says to the other, you know, I think I lost an electron. The first one says, are you sure? And what do you think he says? I'm positive. This one's a little more interesting than 2 sodium atoms walking down the street. I want you to imagine 2 round-bottom flasks. I'm going to pop a hole in each of them. A glass blower can do that. Here's the hole in each of the 2. And pieces of glass tubing were put on. Then the 2 flasks with the glass blower were joined neck to neck. Then one of them was sealed off. The other end, glass blower using a big, bushy, hot flame, collapsed and made a depression, a little pool. And then this, you can imagine, there was a tube sticking out of here. It was attached to a vacuum line. In other words, we could expel all of the air. But before doing so, we injected some water. We colored the water so that you can see. Can you all see this? Can you see the underside here? I have a much bigger one, but I didn't want to bring that. This is about the size we could ship. Then with this water frozen, we pulled all the air out of it. And then sealed it off, just like those vacuum bottles we talked about. So what you have now is an evacuated chamber with liquid. Of course, that liquid evaporates, doesn't it? So really what you've got now is an equilibrium system. You've got the vapor in equilibrium with the water. Now what happens if I put some liquid nitrogen into this depression? You see right away it starts turning white underneath? It's cooking away.
The white, of course, is the moisture out of the air condensing on the bottom there and actually then freezing on the bottom of the container.
And what I'd really like for you to do is to be very quiet, and I want you to watch this side over here.
Did you hear it up here?
There it is again.
Little tink.
Water is an almost amazing material. It exists in, really, H2O exists in three forms: solid, liquid, gas. Solid, liquid, gas. The solid we call ice. The liquid we call water. The gas we call steam. Okay? Liquid water has a greater density than the solid. So the solid forms at the top. And the solid doesn't go through, it freezes from top down. But once you form a solid, then as it tries to go down, you actually hear the ice crack. That's the tinking you heard. Now, if you, Don's already flipped it over, this whole thing is solid.
And we cooled it over here. And that went solid. Explain that to him. All right, have you ever heard of the Maxwell-Boltzmann distribution of energies? It's a graph that you put out when you say temperature that's involved in it. It's really what we find is the average kinetic energy of molecules, right? And so there's molecules of all different kinds of energy that's involved in this. You have this peak that you have that's involved in there. Now, whoa, it went back. It melted.
You see the solid disk.
Now, when we cooling over here, there are molecules that are going through there. Which ones of the ones over here freeze? Isn't it the more energetic ones? And so if you guys had your grades, you know, and we went in and you say, all right, now, I got a series of 5 grades, and I got 100, and I got 70, and 80, and 50, or whatever. He said, we're going to cut out the 100. You'd be a little upset, wouldn't you? Because you took the average, the high one out, and now your average is lower. So if the high ones are going out all the time over here, that's got to leave, but then the average kinetic energy is a lower number. Finally, it gets so low that it freezes. That's the way I explain it.
Taking out the high energy molecule, those that are left have to redistribute, and the redistribution does something like that. You'll notice this maximum here is now over here. The maximum is shifting to the left, which means that the average kinetic energy is becoming less and less. And there's something called the kinetic molecular theory, that kinetic energy is directly proportional to the temperature. And if I can drop that, move that hill more to the left, I will go through the phase change. I have another one at home that we don't ship around. It's made with bromine. And we have the liquid bromine in equilibrium with its vapor. When it freezes, it's different than the water because the solid bromine falls through because it's more dense. And so you get all this bubbling and frothing and foaming. You don't get that pink.
All righty. What about we do something more, get us into room temperature things. Let's do some room temperature things. A lot of things in room temperature are color. Color things. What color is it? What is that back? Yellow? I don't like yellow because it reminds me too much of what my wife makes me go to the doctor all these times. So how about if I change it a little bit? How about that? You like that? All right, now how did I get it that way? Are you not going to say anything to us, not going to talk to us? What did I do? Swirled it? All right. Now how do I get it to go back to yellow? Just let it sit. When I talk to the little kids, I always give them, remember, 3 words. That they have to look, you have to observe. We say you have to observe, look, try, and remember. That covers it pretty good, doesn't it? We call it try and experiment, don't we? And remember, that's the theory that you try to make up so you can remember all those things involved in there. So we know how to get into orange. How to get an orange? Shake it. You told me to shake it, I showed it. Now it's green, huh?
Now it's really red. Now it's green.
Is it going back?
Yeah.
All right, have you got this one figured out?
Now it's red.
What is one thing that it really needs? I'll give you a hint. Air. It needs air, doesn't it? tell you what I put in there. I put in there some potassium, well, of course, I put water in there. Potassium hydroxide would make it quite basic, and then I put in there glucose, a sugar. And then I had two different indicators in there. One is methylene blue, and if you just leave it methylene blue, they call it the blue bottle experiment, where it's colorless and you shake it, it goes blue. If you put another indicator in there, it's called indigo carmine. That's what I wanted to name our first daughter, Charlotte Woodenberry. No, some neat names. Indigo carmine. Methyl blue. Phenol red. They wouldn't like that. So what I have to do is I have to get oxygen into that, react with that sugar, and then these indicators are redox indicators that tell you the extent of the reaction. So if I turn it swirl a little bit, I get one of the indicators to change. And if I shake it, I get both the other indicator to change. And so I get all kinds of colors. When you do it with the little kids, they say, shake it again, I want another color. Let's shake the bottle. You want to shake the bottle later? Come on up.
Now, do we all remember what the active ingredient was? Well, it had to be the oxygen from the air, correct?
Yeah, oxygen and the glucose, for sure. All right, what is your favorite color? Purple?
Pink.
All right, look around you and determine what the favorite color of most people is. What color do you see predominantly?
Gray.
White.
Black.
I see I see two white shirts, but I see an awful lot of shades of blue. Whoops, there's a couple other white ones here. It's a generation. So, let's see if the oldsters can take care of the youngsters. Very loud on 1, 2, 3, shout it out. 1, 2, 3.
We're going to make this turn blue. I'll tell you that. We were on a TV show one time in Cincinnati with Ira Joe Fisher. I don't know if you've ever seen Ira Joe Fisher. He's on New York Station TV now. And we did this at far, and we asked, it's only going to turn blue. We asked Ira, what's your favorite color? And he said blue. And I said, thank you, Lord. and we did it and it turned blue. And he said, well, what if I would have said Paisley? I said, it would have turned Paisley. All right, but we want to show you how regular, how predictable chemistry is. So we want to add these in sequence, 5 seconds apart. And so that when we add the little beaker in the back to the big beaker, jar in the front, that it's ultimately going to turn blue. It's a clock reaction, so it'll take a while. And then we want to add them 5 seconds apart, so that when we do have them all in, and they do start turning color, they'll turn color every 5 seconds. To show you how the regularity is, okay? So we have to count. We count in our classes 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry. Now help me count so that we can help me keep the key.
I think you better go practice running the system.
Because the key is that we got to count fast. And I get excited.
Fast.
Sorry.
No, you want to do fast?
I know. If they don't help me, I get excited and I start counting too fast. All right, here we go. Ready?
Yep.
1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry. There we go. Now wait for that first one to turn. Remember, we got to count the same. Don't get too excited when I do it. Start counting too fast. All right, can you see when it's going to turn? Oh no, you didn't. Let it go. 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry, 1 chemistry, 2 chemistry, 3 chemistry, 4 chemistry, 5 chemistry. Pretty close, huh? Eileen, all stand up. Jennifer is the chairman of the department here at Sonoma State. She's a fabulous teacher as well as an administrator. She and Eileen, who has been the person that has orchestrated our trips all around the Cheetah Hall, they pour those out. And I said, boy, those things don't come out right. And Jennifer says, boy, you put a lot of pressure on me. All right, we did one color that time. This time we wanted to do two colors, and we want our award winner to do our colors. We have special ones from PR. Yes! Yes! All right. We want to do two colors. This is a test here. What is the holiday at the end of this month? Halloween. What's the two favorite colors of Halloween?
Orange and black.
All right. Why do you say orange? What's orange at Halloween? Pumpkin. What's black? All right. This is called The Cat Eats the Pumpkin. All right. It's all yours. Put the two little beakers into the big one fast. Pour them in fast.
Same time.
Same time. Pour them in fast.
All right. Ready?
Perfect.
Wonderful.
All right. Give me a pumpkin.
There.
There's my pumpkin.
That's yellow.
Good job. That was an early pumpkin. Did you notice that? Yellow, didn't it? Maybe we should have done squash or something.
The cat is squash.
Colors are a lot of fun in those. Now, the iodine clock reaction, while Mark's setting this up, the iodine clock is a great example of limiting reaction. Because what you have in there is an iodate ion, IO3 minus, and you have bisulfite, HSO3 minus. And what happens in the reaction, you produce iodine. Now, we also put some starch in there. Iodine with starch makes a blue color, dark blue color. But however, as the iodine is formed, it also sees the excess bisulfite, which returns it back to I minus. So it can't turn blue because it doesn't have I2 anymore. And it keeps going like that, and finally the bisulfite runs out. And once it runs out, then it forms I2, it can't be converted back to I minus, it turns blue. All right, and for the witch or the cat eats the pumpkin, what that one is, you first form an iodide precipitate. Now there is one ion in there, and you have to keep that a secret. And Neil says he's going to take care of it for me. It's a little bit of mercury, but Neil's will take care of it for us, so that won't go anywhere out into the environment. That mercury iodide forms that precipitate, and then the last part is the same iodine clock reaction that comes about. Okay, we did one color, two colors, and we're going to do now three colors.
So we can't do all three in the same flask. So what we thought we would do is ask for your help. I noticed you're a little reluctant here. What are your three favorite colors? Good. This is the American Chemical Society's National Chemistry Week, and so I think it's most appropriate if we were to sing the national anthem. And so, all together.
Ordinarily we stand up. Let's pass that by. We sit down and sing it.
For those of you who want to stand up, you can stand up, but if you can. Oh, say, can you see by the dawn's early light what so proudly we hail as the twilight's last gleam, whose broad stripes and bright stars through the paradise
You guys are never going to make the choir. Stay in chemistry. All right, what color is this?
Pink.
Who said pink? I try to make it as dark as I can. This particular reaction produces hydroxide ion. And so what I had was indicators in their acid form, and then as the hydroxide is formed, it goes into the basic form. What indicator did I use? What color is phenolphthalein? Pink. This one's a cousin of phenolphthalein. This is thymophthalate, which is colorless in acid and then blue in base. Is that okay? That's a blue one, huh?
Yeah.
Now I can't make a white indicator, so I have to make a precipitate. So we put magnesium ion in here. And as the hydroxide forms, we make magnesium hydroxide. And so we get our red, white, and blue. Pink, white, and blue, don't say it.
Well, this next one, we would like to have three volunteers. Do we have any volunteers? One, there's two. There's three right here. Oh, wait, there's three guys? Oh, they keep pointing to this young lady behind you. Would you like to come up? Okay, the three can act.
See, now what are you going to do? You got four. Oh, you're a gentleman, but thank you. We'll get you on the next one or something. We'll get you to do something.
Okay.
Come out and run out here. Oh, yeah, where are people side? You see the goggles? You got them goggles right here? Oh, got the goggles over here. Oh, yeah. All right, let's come right over here. So you can see. All righty. Let me get the... Sienna, you helped me do this anyway, so you know that.
You get the first choice then.
Okay. I called them.
I knew you. All right.
Can you get over on
Yeah,
the
come over here a little bit more in the open area here. All right, now look what Marv has in his hand. Straws.
What are straws for? Drinking.
Blowing.
They're going to be blowing
We're
because
not going to drink it.
Don will tell you that inside these flasks,
Two of them, at least, are indicators. And typically, indicators, if you would ingest them, are laxatives.
and so if you were to slurp this up, you'd want to stay pretty close to
I don't
home.
want to go to the bathroom. All right, would you blow in there first? Don't drink it. Just blow into there. Make some bubbles. All right, let me tell you to the home audience. Sienna, she has one that I put a cup of water, of course, and then a couple of drops of ammonia to make it pasty. And then we have phenol red indicator in there. And we want to see if her breath, carbon dioxide, put into water makes carbonic acid. We'll then hopefully flip the indicator. This is bromothymol blue. This indicator. I'm going to talk about this one in a few minutes. Oh, good. Keep her going there.
Now this white one, Don and I have been working on a new test. It's a
Now
test
you
for
stop.
life. If it stays crystal and clear, with no indication of milkiness, the person's alive. If, however, there's some white stuff in there, then we got a problem. Oof, no.
You're okay.
Really, you know that he's alive. He walked up here, he's got all the evidence of being someone alive. In fact, all of us would have that because we exhale a little bit of carbon dioxide in addition to the nitrogen and unspent oxygen and all the rest. That carbon dioxide with the water forms something called carbonic acid. The carbonic acid neutralizes a little bit of base. Or, in this particular case, we had lime water. So that was already basic. And so here the CO2 works with the calcium ion to form calcium carbonate, which is a solid. So right here, National Chemistry Week, Sonoma College, he precipitated in front of all of you. Let's give them a round of applause.
Gave them each, we also gave her one earlier, a periodic table. What's unique about your periodic table, guys?
It changes colors. It's like a room temperature thing. It makes it change color.
And then how do you make it change color?
You put your finger on it.
Your hot finger, huh?
Yeah.
It's thermochromic. So it changes color when you put your hand. Unless you're dead, like some of the people who was Lee.
Now, Lee Lattery can't get it to work.
Lee can't change it. We're going to have him check that.
You gotta warm up your hands.
All right. Stirring motor. You've seen those in the lab. Probably got a magnet in this down in here. It's on a shaft. It spins around. There's a magnet inside the container that matches the pole. Often poles attract. And so we can stir something up by not having to stir it by ourselves all the time. A little stirring motor. This is kind of nice. It has light in it. It's no water. Put it in here. We're going to give you a little bit of a test. It shows a lot of color, but also it doesn't have an application to everyday life. And then look what we're using.
Anyone recognize this blue bottle?
You don't have to read the label, do you? Milk of magnesia.
Milk of magnesia is magnesium hydroxide, Mg. You take the OH group twice.
And what is the purpose of magnesium, milk of magnesia? What do you do? What do you take? Yeah, it's an antacid that's in there. So
Oh, she's cheap. She went and read the label. It says antacid.
if you had a stomach ache or something, you'd put that in there. Now, why would you have a stomach ache? Well, I'm sure there's a lot of reasons. But one reason is that when you eat possibly maybe spicy food or too much food or something, when your food gets into your stomach, acid comes out. There's messages that sent to your brain, say, send the acid in, help me digest this food. And if you get too much acid, you could get a stomach ache. And so what do you do to correct that? You would add an antacid. Okay, so we want to show you how that works.
This is why it's called milk of magnesia. Doesn't that look like 2% or maybe even 0% milk? The stuff my wife wants me to drink. I call it the blue milk.
So what we see is now when we put that milk of magnesia in there, that some of the magnesium ions actually go into solution, sure. But there's still a lot in reserve, aren't there? There's a lot of solid particles suspended in there. So we have some magnesium ions and hydroxide ions that are ready to go into the reaction. Some sitting there in reserve. If we use up the one, it can come in. Okay, now what do? Well, we like to show you stomach acid, but anyway, I can't do that. So we're going to simulate that. Right?
Before we do
before we
so,
get that.
You've got to indicate, you said this was an antacid. It's against acid. Well, in chemistry, you say it's a base. And the big question now is, how basic is this? There's a scale that we use in chemistry. It's called a pH scale. Kind of like the Richter scale on earthquakes. Small numbers are very acid. Large numbers are very basic. Water itself, neutral water, distilled water, should be about 7. Okay? Well, I have an indicator here, and we've already seen some indicators when the kids are blowing through. Phenolphthalein is an indicator, dimethylphthalein is an indicator, all kinds of different indicators. Mix them together and you get a universal indicator, which is red when it is strongly acid, and it is very dark blue when it's basic. Let's check to see what this is.
What do you think the pH of this would be? Pretty high, huh? Over 10? Yeah. It's actually 10.5. So you see it really being quite hard. Now look at my coat here. Where do you see purple? Way down here. Right? Well, what color do you usually associate with red? Acid, don't you? You know, litmus paper. Blue to red, that's it. Red to blue, out the loop. So we know it's real basic down here, right? It's got to go up here to be acid. All right.
Now for Nils, just to help Nils, pH is about 10.5.
Yep.
I just learned that Nels and I have similar ethnicities, but I don't know if you like lutefisk.
Really?
The lutefisk is about 10.5. For those of you who want to know about it, ask Nels. I happen to like it too.
All right, we're going to add a little acid. I mentioned we couldn't get stomach acid, so we're going to use acetic acid. We're going to use vinegar. All right, so imagine now that this is the stomach and we've eaten something, and now here comes the acid in to help us with our digestion part.
Now notice I didn't put very much in. And it can neutralize. It was purple, now it's red. Well, it's beginning to change already.
What color is it?
Is there any of the milk magnesia left in there? How can you tell?
It's still cloudy. What color is it going to go to?
Remember now, the pH is increasing.
Is it yellow? What color is it going to go to? Green. Give me green. I got green. Where's it going to go now? Blue.
Now I got teal.
Oh, I like that, huh? There's the
Oh,
blue.
there's aquamarine.
And then what's it all be? We completely neutralize what we put in there, or at least had enough magnesium hydroxide to completely get rid of that acid.
That lends itself to a laboratory experiment. It really does. Because I put in a jigger or an amount of magnesia. How much of this vinegar will it take to neutralize all of that? We put in a little bit, And I could continue to do that, but we want to get out of here tonight. Let us think of a
We
Big
want to show
Mac.
you some more things.
How about a Big Mac that's been supersized?
Oh, don't even say it, Mark. Don't do it. Now, there's the red. It looks like it may be a little orange, but I don't know. The red is still pretty predominant, isn't it? Is it still got the suspension? It looks like it's got some suspension, doesn't it? But is it getting more clear? I think it is getting more clear, especially up at the top. It's not changing very rapidly, is it?
Now, you might say, well, doesn't any base work as an antacid? Well, sure it would, if that's all you want to do. However, you'll notice the slowness with which this reacted. And all these reactions are exothermic, they give off energy, but the energy is coming off slowly. The energy is coming off slowly, you can absorb it. So you certainly wouldn't want to use sodium hydroxide. That would be pretty tough on the esophagus, wouldn't it?
Too quickly, isn't it? Too strong, so you get a lot of heat. So we're going to slow process, and that's why we use something like milk of magnesia. Now it's getting pretty clear. Okay, like that?
I think it's time to transition, Don.
Okay. Turn it over. Just try to turn this off. All right. Let me show you a very common concept in chemistry. I want to show you what a catalyst is. Okay? I'm going to show you that. But the idea is that it must be regenerated at the end. All right, so the two stipulations. You must speed up the reaction, and you must have the catalyst regenerated at the end. All right, what I've got is a beaker over here that is at 2 parts. But that's okay, you'll like that, 80 degrees. I wanted it at 70. It's 80 degrees. And what I'm going to put in there is a compound called sodium potassium tartrate. That's called a double salt. Where have we got a spatula? Oh, there it goes. I got it. Sodium potassium tartrate. It has a formula of NaKC4H4O6. Now, the sodium potassium makes that organic part soluble, so I can get it in the solution. But what I want to do is oxidize all of that organic part of the molecule to CO2. That's typically what you do with an organic molecule, can't you? You oxidize all. We do that. We can get all kinds of organic compounds, and we get it back out CO2 and water out of that, don't we? All right, so I'm making that sodium salt I was able to get dissolved. It's nice and hot. Now what I'm going to do is pour in there some 30% hydrogen peroxide. 30%. Now what you buy in the drugstore is 3%. And you put that on a wound to clean it out, don't you? And when you put it on the wound, what happens? It bubbles. Now the bubbles happens because we're decomposing hydrogen peroxide quite quickly because of the catalyst in the hemoglobin in your blood. And that takes the hydrogen peroxide, H2O2, to water, H2O, and oxygen. And the oxygen, what you see is bubble, and that's the cleansing action of the hydrogen peroxide. It's in, I got 30%. This does not clean a wound, it makes a wound. It's on your hands. I'm glad Mark poured it for me. All right, now, I'm going to put that in there and watch this reaction.
Wow! Yeah, done it again.
Now, I know you won't be convinced, but it is decomposed. It is reactive, but it's very slow. And so what can we do? The first thing the students will tell me is, heat it up. Get that Bunsen burner out and heat it up, huh? And I've already heated up to almost 80 degrees. So it's very hot, and so it's still not doing anything. So what I can do is add a catalyst to it. And the catalyst in here is the cobalt ion, cobalt +2 ion. It doesn't seem to matter too much the concentration. We just throw a little cobalt chloride in there and be able to just dissolve it in water. And so you can see I added not an exact amount. So I'm going to put some cobalt ion in there. And what do you notice already? A color change. And do you notice the bubbles? And so the reaction is speeding up.
What are the bubbles?
The bubbles that come up are carbon dioxide. It's in there. And the reaction is also exothermic. I hope it didn't do it too much. And so as it gets more and more hot, it gets faster and faster. And look, the reaction is going pretty good now. see, if it is indeed a catalyst, it's got to go back to the rose colony. Isn't that cool?
So today you can say, I have seen an activated complex.
All right, now tell me the two requirements for a catalyst. One, what does it do? It brings out the reaction. So what's the stipulation? It must be regenerated at the end. If you remember this demonstration, you'll never forget that definition.
Now that was an example of a homogeneous catalyst. Everything was going on in one phase, namely the liquid phase, and of course the product was the gas. I have a slightly different problem here. I can't get that bottle into that little beaker. Any suggestions? Get a different beaker. Make this smaller.
Get a bigger beaker.
We could perhaps make this smaller. One way to do that, because of the nature of plastic materials and the long chain polymers, is to place a little bit of that same hydrogen peroxide in here. That's the 30%.
All right, what's the formula for hydrogen peroxide? H2O2. And what would it rather be? H2O. Much more stable compound. So it will decompose. It's decomposing now. In fact, if you have hydrogen peroxide at home that you use for a cleansing agent, like you ladies, clean out your ears, you know, when you have your earrings and so on, keep it in the refrigerator. That'll slow down the decomposition. But it doesn't go really fast unless you add a catalyst. Now here's a heterogeneous catalyst. This is that's dangerous when he looks up.
But if you look at the periodic table again, a few moments ago, Don used what as the catalyst? Cobalt. Cobalt. It's in the first transition series. I have another that's frequently used as a catalyst. This happens to be the magnesium, or the manganese ion. And it's manganese dioxide is what I'm happening to use. And what was the formula of the stuff inside here?
H2O2.
Okay, and what did you say it wanted to be?
H2O.
So that means it's going to have to lose what? It's going to have to lose an oxygen. Let's see if we can't do that. Oh, great genie! Great Scott! It fell into the bottle. The bottle fell into the beaker.
The smoke detector up there.
But this is not smoke.
It's just
I know this is not smoke, but it
can't
comes out of there.
Yeah, this isn't smoke, is it? What is it?
Steam.
You can't see steam.
Can't see steam. Steam's invisible.
Water vapor, condensed water vapor. And so he's writing the reaction, H2O2. He added a catalyst. It's manganese dioxide, or manganese dioxide.
Manganese or oxide.
Oh. And now is that balanced? Is that anything wrong with it? What's wrong with it?
2 hydrogens, 2 hydrogens. 2 oxygen, 3 oxygens.
Change this to a 3.
Okay. You want students to do that?
There is the Lang-Showalter theorem, and that is, or it's actually a commandment.
There is more than the 10 commandments. There's 11 commandments.
Thou shalt not change the little numbers. So,
What do we have to do to balance this?
we got a finagle.
I think let's put a 2 out here. Right? And now I got 4 hydrogens. Make 4 hydrogens. How many oxygens I have? 2, 4. And I have 4 here. I need 4 over there. Do I have a balance?
Congratulations.
Thank you.
10 points.
Okay.
But you'll notice the bottle got a lot smaller. And of course there's a lot of heat generated. So what if we were to do the thermodynamics on it, we would place plus heat, wouldn't it? We call those kinds of reactions exothermic, do we not? And so we catalyzed this exothermic reaction. And it's what kind of a reaction? A decomposition reaction. So right here, National Chemistry Week, the exothermic decomposition of hydrogen peroxide, catalyzed by manganese dioxide. And if we were using a Coke bottle, we would find that the label comes off, so we're environmentally correct. We can separate the two, and we can discard them properly.
I'm gonna take a little break of hot for just a second. I want to definitely do this one this time. This is what it's not hot, but we have a purpose for doing this one, as you will see in a minute. All right, what's in this? Air. Air. What's in this? Air. What's in this? Air. All right, so you got 6 cups, and I have one back here. What's in this one? Water? Looks like water. It is water, actually. All right, this no longer has the water in it, right? You ever play this game?
Now, you should know that Showalter actually lived in Louisville, Kentucky. He went to the University of Kentucky in Lexington. He needed to raise money. He sat there on the campus and was doing this. Okay, which one has the water in it?
One left.
I gotta get your pickle this way.
All right.
It's not this one?
Are you sure? Are you sure? I'm sure. I hope.
No, it's so nasty.
What about this one?
No.
No?
It must be in this one. It's not in there. Not in here. Not in any of these. Where'd the water go? Okay, well, let me show you. I won't tell you.
No, let's have someone else.
Let's show you. That's right. And I know just the person. That's why I'm doing this. He knows who the person is, too. Oh, come on up here.
Okay.
Here's your glasses. All right. What we got to do with that one is we got to put some powder. Let me put the powder in for you. We usually have a little vial with it already in there, but I couldn't find it. So I got a little powder here that I can put in this. It's called water lock. And I don't put very much, just enough to cover the bottle, so it's in there. Now what Paul to do is pour. You're right-handed, aren't you? I'll switch it for you there. Paul, I want you to pour all of that into that jar in 4 seconds. So we're going to count really fast. Ready? We're going to count. Go. Okay. 1, 2, 3, 4. Oh, did a good job. All right. 4 seconds he poured in that. Just want to try it again? All right, pour it back. Let's try it again. Pour it back, Paul. What happened?
Something locked up.
It gelled, huh? Have you seen that before?
Yeah.
That's the water lock. You've heard of that water lock before? It's in there.
Thank you.
And you made a nice mess here, Paul.
I don't like
All right, now, do you know how this works here? That's right. What did I put in this one cup? Some of that little powder. Right, so there's the water locked up with that powder. Anybody know the name of the powder?
Water lock.
It's water lock is the commercial name. Sodium polyacrylate. Sodium polyacrylate is the powder. Now, what is the common use for this powder? Diapers. What else? Space suits. Again, for that same sort of purpose. I don't think any of you as old as I am. If you remember when my kids were small, I have grandchildren now. When my kids were small, we used cloth diapers. And it was a mess. We changed the diapers so often, and we were always either changing diapers, washing diapers, putting them back on the baby. It was terrible. And then they finally came up with these Huggies and Pampers, and they didn't have this powder in them, but we changed them quite as often, but just 2 in 1. It was in there. And then finally they came out with the powder. And when they were doing the trials of this, they did it with the diaper as flat as it was originally, and it caused rash with the baby. Of course, this is really absorbent. This powder will absorb in pure water 1,000 to 1. It is 1 gram of this powder will absorb 1,000 grams of water, pure water. Now, our urine is salty, and salts will compete with this in terms of being able to tie the water up. As a result, it's about 60 to 1 in urine, which is much better, so you don't want it to be too dry. that's involved in there. So when they made the diaper nowadays, in the last several years, they made it as a honeycomb. The diaper's quite fluffy. And that powder is distributed through there evenly, and then the absorption happens at an even rate that goes in there. And when our kids, our young grandchildren went to daycare, they would keep records of when they changed diapers, and they'd be there maybe 4 hours and change diapers a couple times. That's it. They'd change it 50 times by the time it seemed like before. And so, but I can make you a diaper last all day. If I put enough of this powder in there, it's going to last all day. But what's the trouble with that? It's too heavy. And they won't be able to move. We had a friend that had a little baby that had nothing more in the summertime than one of these diapers on with the super absorbent in there, and she jumped into the little pool. He went to get her out and couldn't get the kid out of the pool. So you have to use the engineering sense that goes along with it. Okay, I'm sorry. I want to get Paul involved in that. Okay, what's the next one?
That's what it is, lab coat, isn't it?
I say, what's these colors? What do we say? Roy G. Biv, right?
And it's the red, if you take white light and separate it into its components, I think we've all seen rainbows and imperfections in glass and maybe get the colors out. Here you got the blue is the highest energy, because it's the shortest wavelength, and red is the longest wavelength, and by that I mean it has smaller energy. On the other side here, I have a screen that's now being exposed to light. Okay, it's absorbing light, the white light. If we were to turn the lights off, we can get them all off nice and dark in here. Now keep your hands to yourself. Can we get those off?
Whoa, there you go.
Whoa.
There we go.
Is it glowing?
It's going!
It's glowing. Excellent. Excellent. I'd like to illustrate that. There is a new, or a series of, hang on. I have another one of those things here, but this has not been exposed to the light yet. Do you have a source of white light, Don? I'm going to set this one over to the side. I've got one of these little lights that you can use for a keychain. Notice this. You see, it's absorbing light. Now, what color of light do you think it's absorbing? White. Well, light is made up, we said, of all those different wavelengths. It's emitting green, isn't it? Like we saw over there.
So white light. White light has all wavelengths of light. So some of those wavelengths are making light, some of them aren't.
What color is this?
Red.
Let's see, does red absorb?
Yes.
It is? No, this is the white from before. This one is yellow.
Orange.
Or orange, rather. And the orange does not absorb. And we have yellow. See, all we've got is that white left up on top there. And now this is green. Let's see if green will do it. It's very faint. I can see very little. Very, very little. And now I have a different color. I wonder if blue will absorb. Oh, blue is a, so blue is high energy compared to the others that we've done. And this is the last one.
Let's hear it.
Okay, here we go. National Chemistry Week. See, all of this is some film, some plastic film that has been impregnated with particular molecules, and those molecules will fluoresce when excited. So while this is, you might say, hey, that's a physics experiment. No, it's not. Everything is chemistry. Everything. The interaction of light with matter is chemistry.
Where's your LED?
Well, we wanted to finish this thing off by doing hot things. And one of the things that we can do...
We'll do a little explosion. Yeah, let's do a little explosion.
What do we need?
All right, what do you need for explosion? A bomb. No, we don't want a bomb. We want just the basic idea. All right, look. Now when you hear about a fire, because the fire, have you ever heard of the fire triangle? All right, fuel, oxidizer, spark, right? And they say if you don't have any one of those three, then you're not going to have a fire. Agreed? All right, now how do you make it into an explosion? Need one more thing. A closed system, don't you? So when the fire starts in that closed system, it causes an increase in pressure, and then you have an explosion. So the only thing we need differently, Marvin, is a closed system.
Closed system. Well, I spared no expense. When we came to Sonoma State, when I heard we were doing that, I went out and bought a polymer. Polyethylene. And you've been telling me so long, what should I do?
Put a truck in it.
Okay, so there's the seal system.
Okay.
What else you want?
Fuel.
Fuel. We got a little bottle here of methyl alcohol.
Methyl alcohol, that'll work.
Okay.
That's the fuel in an Indianapolis 500 race car.
So you want me to put that in here?
Put that in there.
Okay. So I got a little bit of that.
No, hold it too much. Okay.
What else?
And we need a sparker.
A sparker. I have a sparker. It's
Right here.
a cattle prod.
No, that's called a Tesla coil.
Yeah, that's what I do with physics. This is a cattle prod. And if we can kill the lights again?
See that spark?
What color is it?
Can you see up front what color it is? Kind of purple. That's because we're exciting the nitrogen atoms in the atmosphere, causing an elevation of the electrons, and it's coming back down, but giving off the wavelength of light, characteristic of the structure of the nitrogen atom.
I'm going to bring this thing closer and closer and closer. You tell me how close I have to be.
How close does it have to be?
Okay.
How much?
Turn them up.
2.54 centimeters, please.
All right.
Now, if the wires touch, what happens? They'll spark, huh? If it's too far apart, you can't jump. And so it has to be less than 2.54 centimeters.
Yeah, I've got a sparker.
All right.
I've got a container.
All right.
I've got, oops, let me check. Yeah, I got fuel and I've got oxygen. Yeah, I got oxygen in there.
You saw oxygen?
But I saw air.
Oh.
Okay, let's see if this will work.
No, it's not going to work. It's
Why?
plastic. You got to get a
I've
spark.
got the 4 things that you told me.
You got to get the spark inside the container.
So you want me to do some engineering additional?
So we need some metal, right? Get some metal, make a spark gap. Where do we hear of a spark gap? Where do you, in your spark plugs, huh? And if the spark plug that has the wrong gap, it won't work, will it? If it goes shut, you're done. You're not working. All right, you ready?
Yep.
All right, how far is this spark?
172.
1.72 centimeters apart. All right, that's 2.54. All right, here we go. Put it. Where's spark? On the metal.
Oh, in the metal.
That worked good.
By the way, we're on a low budget, so if you find that
That popped pretty good, huh? All right, let's do it again.
part, now you know what's coming, so we don't
What do
have
you
any
need? What's the four things you need? Fuel, spark, oxygen, container. All right, put it on there. Whoa.
Oh, here.
Whoa!
Good. We got a good one.
We got a repeater.
One more time.
Now you're dead.
I broke it.
What's wrong?
This thing's working.
Out of fuel.
Do we still have a container? So what must be missing? Okay, we got 2 different schools of thought here. We hear that it's fuel, or it could be the oxygen. Okay? What do you see, Professor Shaw?
I'm testing it. It's got fuel.
Oh, so it's missing what? Oxygen. Okay, sure. You have some?
I'm all out. You do it.
All right, hang on.
What's with the leg?
Every time I blow, that's what happens.
Got nothing there? All right, now this is also a good experimental not only for the explosion part of what it needed, but also for the scientific method. You think of the scientific method, what's the first part of the scientific method? You recognize the problem.
Are we done yet?
You're done.
Now, some people say, hey, you can't do that, you're putting in CO2. Oh, wait a minute. The air that you're breathing is 79% nitrogen, about 21% oxygen, a smidgen of everything else. CO2, water vapor, pizza breath, anchovies, whatever. But when you exhale, I just went to the doctor recently, and he said, you know, Lion, you're in pretty good shape for the state of the earth. What you are doing,
No, he said you're in pretty good shape for as old as you are.
the thing is, I'm metabolizing 15% of the available oxygen. That's pretty good for an old guy. And I thought about that. I'm metabolizing 15% of the available, 21%. That means I must be exhaling something. Let's find out if we did.
You're exhaling the nitrogen in the air,
Yep.
right? And also any unused oxygen. All right?
Are you ready?
I'm ready.
We got a couple of deads up here. Let's see if we can make another one.
Yeah, you really broke it.
All right, you here. Let's get some real young guy oxygen.
He didn't squeeze it.
So you have to sometimes, you know, really squeeze it. You got to really kind of
CPR.
bond a little bit. He teases me about my leg.
All right. Let it happen, Captain.
You know, I
1.72.
didn't check the calendar. I
You
mean,
check the gap.
172.
All right. Let's see that this time. If it doesn't work this time, we're dead. Holy moly! It works. All right. Yeah, I'm talking about the scientific method. First thing you recognize is the problem. Then what you're supposed to do is study the problem. And we've studied it. We know what core components are needed. Then what's the important thing you come up with? It starts with an H. Hypothesis. And what did you see? Did you hear the hypothesis? Naturally coming out of here. It's out of fuel. It's out of oxygen. And when we test, the next step is to test and see. And then we experiment. So you can see the whole steps of the scientific method with that little bit of experiment there. Okay. Now, I don't know, Mark, we think we ought to really do this. Have you ever seen this? You want to do it?
Was that an explosion on the little cork?
Jennifer, are you all right with this?
Go for it.
Rotate the center, I think.
All right.
We're going to put some methanol in there. Now this one we can't cork. We don't want to cork. We want you to see what happens inside.
Because it's not an explosion. Everything I'm going to do is not an explosion. They're implosions. That means it goes in.
Dr. Shirley.
What's he doing? What's he doing now? Vaporizing the methanol that's in there. Methanol has the characteristic of being volatile. We think of volatile as being exposed, and that's not necessarily true. It means it goes easily from the liquid to the vapor state, doesn't it? It usually has a low boiling point and a vaporization high that's in there. So what we're going to do is, once he gets that nice and vaporized, I'm going to drop a match in there. Stupid old me.
I'm going to have you turn the lights off.
You'll turn the lights off for us.
But I'd like for you to be very quiet and listen. You hear the...
Hear anything?
See, I'm vaporizing it. It's building up pressure in here. That's why I have to get my hand away from this thing.
You sure that's the...
Ready?
Sure that was what it was? All right.
Ready?
What? No, I can't. Wait a minute, don't take it off. I can't see the old. Now I can. Okay. All right. Turn it. Let her up, buddy.
Keep going, keep going, keep going. It's dancing. Now you saw that this came in, not going out. It's not an explosion, it's an implosion. And the reason it pulsed like that is it started burning at the top. Then it pulls in some more oxygen from the air, pulls some more, and it worked its way down.
And typically we add up methanol that is not all vaporized. And so as it reacts, it's getting more fuel to add to that, so it stays in there for quite a while. The dancing flame.
Do it again.
Want to do it again? Yeah. I don't think I can blow it up. I'm surely it's out of oxygen as well as probably out of fuel too. We call that the whoosh bottle.
Did it whoosh? We have just a couple more. Hopefully we keep you.
You'll keep about 5 more minutes? 5 more minutes. Have you ever seen Wrinkle Your Chips? We call it Wrinkle Your Chips because we use this can, which we had to sacrifice our body and eat all. And I tell you, Eileen loves chips too, so she helped us. All right, what we did is we took the Pringles can. Now you borrow just a second. And in the bottom of it, we made a small hole with a nail, like a finish nail. And in the bottom, I usually cut a hole a little bigger than that, but I usually cut about the size of a quarter. All right, now what we're going to do is we're going to fill this full of hydrogen. Okay? And we'll make sure that there's no oxygen in there, no air in there. And so you have to purge it out with hydrogen. You ready?
I'm ready. You talk.
And then we're going to set this on here, and I'm going to light that hydrogen on the top of it. It burns. Hydrogen is an excellent fuel. It will burn very clean, and of course, when it burns, where does it go to? Water. So there's no pollution that comes about through this. If we ever have hydrogen in cars or something like that, supposedly we would not have pollution in that. All right. Now, what we're trying to simulate is the space shuttle. So the space shuttle has hydrogen and oxygen in there, and as it reaches that ratio of 2 hydrogens to one oxygen, volume-wise, it will cause an explosion.
You ready?
All right, let me explain one more thing. As I light it, remember it has a hole in the bottom. So as it burns, it's going to be drawing air in the bottom. And air, of course, has 21% oxygen. So as soon as the oxygen and hydrogen ratio becomes proper, liftoff!
Here we go.
Don't do it. Let me get my match going. You ready? Did you get all the oxygen out, Mark? No, a little bit up forward. No, it's still not on. Okay. Don't take your finger off. Here we go. All right, turn the lights off, please. See it burning? All right, now let me tell you that it will make a loud noise. Don't worry until you hear the whistle. What happens is, as it burns, the hydrogen burns the hydrogen, the flame gets down lower and lower, and starts bringing in a little air in the top. And it makes a whistle. When you hear the whistle, fire in the hole. All right. Well, you filled up good, Mark. Is the flame getting smaller?
Yeah.
Listen, whistle. Here it goes. Liftoff!
I mean, that's not part of the patent.
That's Wrinkle Your Chips. We got one more. That's it. Oh, we got some more of that? Oh, what's right?
Harry's going to kill us.
Harry. Oh, Harry went down. Harry's got to kill us if we don't do
So
this.
that's the last one.
Okay.
We're going to do these first.
What are we going to do first? Oh, okay, we got one more. We're going to do the balloons for you, and then one more that makes a little smoke, then we can hop out here. Huh? Okay. Now, what's in the balloons?
You'll notice that they are lighter than air. Obviously, they're gases. Purple's kind of cool, isn't it?
Some people really don't like balloons. I don't blame them. There are some people that just can't stand balloons. That's okay. I understand. Now, what we have in this balloon is helium. Helium is an inert gas. And so what we're going to try to do is ignite the gas in each balloon and have you tell from the sound of it how different they are. This is an inert gas. So you can imagine now what's going to happen here. Hold on, Mark. All right. All right. that old balloon there, Mark?
One of the things in chemistry, you always burn things just to perhaps get some idea of what's in it. Is it flammable or not flammable? This is helium. Is it flammable? No. Let me prove it. See, it's a
Nothing
fire
more,
extinguisher.
nothing more than the sound of the breaking of the balloon. All right, this one out is yellow, which yellow means caution. All right, so this one has some hydrogen in it. Low enough, you think? A little lower? All right, now lights off on this one.
I need
Oh, okay. Need a light? Don't hold your ears on this one. I wouldn't tell you wrong. I promise I won't want to surprise you. But this has a beautiful sound. This is very low, not piercing to you at all. So you don't need to hold your ears on this. I love the sound of this. Okay. This is hydrogen. You hear anything? A lot of fire, right, but not much sound. The low sound that's involved in there. There's a little bit of sound because of the oxygen in the air. Mixed a little bit with the hydrogen causes a little bit of sound in there. But we can enhance that sound. Red means danger. And so this one has hydrogen and oxygen in it.
This one will be like a shotgun. You know, one of the-
Or louder. We want everybody to hold your ears on this. Now when you hold your ears, don't put your fingers in your ears and hurt your ears. Always put your hands like this. Now you people up front here are going to feel it on your chest too. Hold your ears. Everybody, you won't do it unless everybody holds their ears. All right, everybody, hold your ears so we won't do it, then everybody won't hear. All right, got it? All right, here we go. It's hydrogen and oxygen. Really got it. Feel like you're on a stage. Up a little bit higher. I can feel that stage. The shock wave comes out of that thing. All righty. Did you hear it? Did you feel it?
And I've done it many times too.
I don't think it's up here. This one I bet you haven't seen. Many people have seen this one. This is a reaction that we're going to do with dry ice. We got 2 blocks of dry ice. And we have carved out a little bit of a pit in one of them. And we're going to put magnesium turnings in there. Have you seen this? Magnesium turnings. And we're going to put a little bit of magnesium ribbon in there that's a little smaller particle size so we get it started. We're going to get the magnesium burning, and then we're going to put the top layer of the dry ice on there. So we're going to see this reaction inside dry ice. Now, dry ice has a sublimation temperature of -78 degrees Celsius. Very cold inside this. You'll see this reaction it actually gives off some other kinds of energy. You'll see. How you doing, Marvin?
I'm doing just fine. Keep talking.
All right. Let me show you the reaction, and then we can see what happens in there. We have magnesium plus carbon dioxide. Okay, now this is a solid. This is a gas. And it's going to reduce the carbon dioxide. It's going to take all the oxygen out of the carbon dioxide and go to carbon. I had a great question from a student the other day. He said, "Do you think there's buckyballs in there?" And then it gives you a white powder of magnesium oxide. Is it balanced? What did I do? I need to change the little numbers. Did I put a 2 here?
Yeah.
All right, and a 2 over here. that get it? Okay. And so what you're going to see when this ultimately happens is we'll have black carbon and white magnesium oxide powder formed. You also get some nitrogen. You remember when you do the experiment, if you do the experiment where you burn the magnesium, you have to take a little water to get rid of the nitrogen, magnesium nitride. Marvin, what are you doing over there?
Doing what you just said. I got some solid carbon dioxide, dry ice. I'm going to put some magnesium metal in the form of magnesium turnings. Organic students, organic professors will probably remember a time when they were asked to, do reactions.
Right against the wall?
No, we're going to do it over there. Magnesium turnings were used in the Grignard synthesis of alcohols and so forth. And you know, it's harder and harder to find the turnings. They're only selling powder or granules now. The turnings were very nice before. To show you what's going to happen, Don has...
There it is. I put some of the magnesium wire, the strip inside that pile so that we can start with that.
Well, I thought I'd show them this. I need to have this lit.
Okay. What do you do to get a match going? Some people say strike it. I don't like that. You don't just set a match down and strike it. It doesn't work. They say light it. That's what I like. It doesn't work. You activate it.
Activate my torch.
You activate. Knock the head of it off.
Cheat.
You get it over the activation energy barrier. All right. What do you do to this torch? You don't light it. You activate it. What do you do your Bunsen burner? Light your Bunsen burner. Activate it. All right, you ready?
Here's magnesium metal, and you can notice it does heat.
Don't look at it right away. Look at the size of it.
Extremely bright. I'm just going to drop that in here in this hood. That's what we're going to do with the stuff that's now sitting in that block. And so that it's close to the hood, and we've got a good downdraft hood in here. I'm going to light, or try to get that metal that's in that little pocket. I'm going to try to get that metal to be heated enough so that it will ignite.
Where's the other piece?
That's right next to it.
Oh, there it is. Where's my
I'd like to get that to ignite. Once I get it ignited, we'll put this other piece on top of it and try to put it out. And I guess those people over there can't see. Okay, here we go.
Can you see that?
I need to keep it as close to this hood as possible. This will be our final demonstration. And Sienna's been handing out little cards for the business of educational innovations. Make sure you drop those off either with her or with Don or with me. It's just about going, isn't it, Don?
It's just about there.
I'd like to see it, that same white. There we go. Lights.
Lights out. Oh, Marvin, did good. Did good. Oh, come on, baby. All right, come on.
Okay, back up.
Back her up.
That's what happens when you're in a hurry. You got an audience that wants to go home.
Yeah. Come on, baby. It's getting hot. I'll tell you, this block's getting cold. We should have put more wire in there, huh?
Try it. Try it. No? Okay.
One more time? You want me to put some wire in there?
Magnesium's here.
Yeah. Paul, can you? There's a wire right here.
No, not water. Just put some of this in.
You think it's too hot to put the wire in?
Well, if a little works, a lot's a lot better. That's not true.
It's hard to get the turnings really hot enough. Oh. 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 Come on, baby. There it goes.
Holy moly, look out! It's trying to put out the CO2. The CO2 is trying to put it out. But the magnesium wants that oxygen so bad, as Don had it right here, it tears the oxygen right out of the CO2. The magnesium does. And that'll blow for a little while. And as he said, the carbon that is formed is carbon black. Embedded within that carbon, I'm sure that's a nice experiment if you can figure out how many buckyballs are in there. And there's also possibly some diamond. Is that another allotropic form? I don't know if there are other forms. Carbon black or graphite.
I've never seen it last that long. It really lasted long.
Well, we had quite a bit of stuff in there once again.
Oh, it's alive. Look, it's heartbeats.
It has truly been a pleasure being your demonstrators this evening. We really appreciate your coming and staying this long. And again, we'd like to wish you happy National Chemistry Week. And next year, believe it or not, is International Year of Chemistry. Several years ago, it was International Year of the Child. It was International Year of this, that. The international science community has determined that 2011 is the International Year of Chemistry. The American Chemical Society has 365 days set aside to illustrate and to celebrate chemistry. And we hope that you'll do that. Bonnie Carpenter, thank you for being here with us tonight. And I hope that the ACS will continue to fund or at least be involved in activities like this throughout the local sections of the United States.